share the screen. Is this are the slides visible?
Yes, sir. These are visible.
Okay. Okay. To start with, I think there was some confusion that got created in the last class during the discussion, where Sampark asked a question regarding the implementation of threads in the Linux operating system, and what I essentially told that Linux uses user level threads, and which is not capable of exploiting the multiple cores in a dual core or a quad core CPU in a system. So that was partly correct statement. That I'll be that's why I'll be repeating some of the slides, and I'll rephrase that statement. So that will be the first few slides will be on that, and then we'll see that how that pthread library gets implemented, and we'll see some existing some examples of creating threads using the pthread library. So to start with, and to get the rephrase statement first, Linux uses pthread or POSIX thread library. So this POSIX thread library is not an implementation. Okay, so that is the mistake that I made. I didn't distinguish between the implementation and the interface. So pthread library is a POSIX thread library interface, which gives you a set of standard way of calling functions, library functions, user level library functions, to create, synchronize, then terminate threads or exit threads. So those are there, and because it's a standard that is maintained, so if we write our pthread, our applications, threaded applications using these pthread library functions, this will be portable across multiple platforms, multiple operating systems, or multiple kernel implementations of the same Linux, whatever. Now this pthread never attempts to define how this creation will actually take place, or how the operating system kernel will handle it. Okay. Now in Linux, there are multiple, I mean, at least there are two projects which attempted to come up with some implementation of this pthread library, whatever it is there. So pthread is a user level library, and there are two projects. One that was Linux threads. It was, the name was LINUXTHE. So Linux threads is the name, quote unquote, and the another was NPTL, that is native POSIX thread library. Okay, so first came the Linux threads, and in the Linux threads, they are, I mean, that was the first attempt, and the author name was also there who wrote the library that time. It was in early 2000, and almost in the same time, uh, but it was a library which attempted to implement the internals, that how the kernel is going to handle it. And the major issue was, if as a user you create corresponding to your process 3 user level threads, so what will be the view of the kernel? So how will the kernel uh, be able to see the existence, or will it be aware of the 3 threads, or it will be just looking to the process itself? So there are some debates, or maybe the 3 threads in the user level will be mapped into multiple, say 5 threads in the kernel. So how this mapping will be done, that was a debate. And Linux, in all its implementation of the thread library, it considered to be this implementation as a one-to-one mapping. Okay, what it means in the pthread create, in the using the pthread library, using pthread create function, we'll see shortly. If I create 2 user level threads, so that pthread library is using NPTL, so which in turn will try to create 2 kernel level threads within the Linux. Okay, so this means the confusion that was there, the pthread library, the threads are not visible in the kernel. This was completely not true, and I apologize for that. So that was a wrong statement. So please correct it. So this Linux, what it does using NPTL, it has got a one-to-one mapping of all the user level threads. So if you have got created 3 user level threads, they get implemented internally within the kernel as three identifiable and distinguishable threads within the kernel, and the kernel actually schedules these threads. But the catch is Linux does it using some other system calls, like so we know that for process creation we have got the for, but while it is trying to create threads, it uses another system call called clone. Okay, and clone has got multiple ways of creating a child process, and one of them is used to create such threads. And to be specific, Linux does when it does so, it prefers to call it as a lightweight process. Got it? So Linux, using the clone system call, whenever you call pthread create in the user level library, internally it will uh, call clone system call, and the clone will create a lightweight process corresponding to that pthread create, and that lightweight process is basically the thread which is identified by the kernel. And like any other process, each of these lightweight process, or you may call it as kernel thread, whatever, these are schedulable. So once this happens, that means all the three threads that you have created in the user level using the pthread library, which is a user level library, are actually schedulable independently, and they will be able to exploit the existence of multiple cores or CPUs. Okay, so that means if we write some application using pthread create, using pthread exit and whatever pthread library, they indeed all the threads can be simultaneously scheduled across multiple cores or processors, and there is no there is no problem as such. But the point is, when in the right from the beginning, when the concept of thread came in the mid 90s, in fact those days there were no this multi-cores machines. There is just a single processor, and the initial thread libraries, even the POSIX thread library, didn't have much options, and in a single core processor, creating multiple threads does not necessarily make a lot of sense. Even creating multiple childs also does not make a lot of sense. So you are not able to exploit the parallelism until unless you have multiple threads in the running state. So uh, if you have got 2 3 threads running in the running state, until unless you have got multiple CPUs, you cannot run them parallelly. So in a single processor machine, which was in the late 90s or during the 90s, most of the machines are having single CPU. So the multi-threaded concept was just a fancy imagination. It didn't had that much of impact. But from 2000 onwards, mid of 2000 onwards, once the dual core, quad core machines, desktops uh, came, the threading became very much useful, and accordingly thread libraries also got changed. The different implementations came. Okay, so I'll be just so this is a whole story, and because there was there was a confusion that in fact got created. So in support to this, I have modified some of the slides, as well as I'll be coming up with the examples where we can show the existence of the threads.
Excuse me, sir.
Yes.
Sir, but in Linux, there is no concept of a thread, right, sir? Even
Yes,
thread is implemented as a process.
yes, just now I mentioned. So what actually it does when you attempt to create a user level thread using pthread library, I'll show you. So you are calling that I want to create a thread. So internally what happens, it calls the clone system call, and the clone system call actually it creates a lightweight process. Got my point? So it's a lightweight process. So this lightweight process, will see the difference. So this is a lightweight process in the sense that with respect to the parent, it will not have a complete independent existence. It will have some sort of dependencies with the parent from which it is getting created. So that lightweight
Sir,
process, yes.
sir, but there is no different data structure for a thread, right, sir? As
Yes,
far
it is
as I
there.
have read.
It is there in the Linux. It maintains. It is in terms of the task structure. So in the task structure, in fact, Linux talks about worker threads and all this. It is there. So it may take another maybe. I'll take another week time. I'll discuss the data structure also. Okay. So there are indeed, but within the process structure itself, it has got entries corresponding to the threads when it maintains. But again, Linux, it is often identified as a lightweight process. In fact, using the PS, I'll show you what a lightweight process is, and when we create, how it actually, in turn, it actually creates a lightweight process. We'll see
Sir, so
that.
the scheduling overhead is not the same as a process.
See the scheduling, as I mentioned. So once you create three threads, all are visible in the kernel. So the kernel is actually, it is scheduling all the lightweight processes. Okay, so normally when you don't write a threaded application, you just write one process, and one process means this, you can consider that one process, one schedulable entity. When one process creates multiple threads, so process itself is there, the process, the original thread, and three additional child threads it creates. So each of those child threads are considered to be lightweight processes. So it's a heavyweight process under which there are three lightweight processes. So all these four processes, the heavyweight one, which is a parent, and the corresponding child threads, which are considered to be the lightweight processes, all the four entities are schedulable. What the point? But the advantage is, when we switch between these threads, these user level threads, which in turn actually switches between the lightweight processes, the switching, context switching becomes very fast. That is the advantage.
So
And
that's
if
what
you,
I'm wondering, sir. Sir, how is it
yes,
possible to reduce the overhead if the Linux kernel identifies process as the entity?
no,
Because
no, that is
however
what I,
thread may
that is what I mean. Linux process schedules, you can say it schedules a kernel level thread or a lightweight process. But when there is no thread, the heavyweight process itself is identifiable. But when it creates multiple threads, it creates multiple lightweight processes. So including the original heavyweight process, these lightweight processes together are schedulable. So the data structure makes the provision for that. And maybe
okay, sir.
within another one or two classes, I'll come up with the data structure itself. Okay, so Linux maintains, so it is not exactly the way the process control block. So within the process control block, it makes provision, there is a task structure. Within that, it keeps track of these lightweight processes if you have created, so using the clone. So the existence of clone system call, it is not dependent on the thread, but using the clone, you basically or Linux basically implements the thread library, the user level thread library. Is that clear?
Okay, sir.
I think when the examples are shown, it will be much more clear. So that's why I say, so Linux, it indeed identifies processes as a schedulable unit, but this lightweight process is also a process. We'll see this. It's also a process, but it has got some overlap with respect to the heavyweight process through which it has been created. That's the point. So until unless the data structure is evident to you, it becomes always difficult to uh, map that to how it is actually done. So maybe, as I mentioned, so give me some time, I will come up with the internal implementation to a certain extent. Okay. Hello.
Yes, sir.
Hmm. Sampark, are you there?
Yes, sir. Thank you for the explanation, sir.
Yeah, so let me continue with the rest of it, so that uh, I think it will be clear. And I have forwarded the book by Mikhail Kerish, and in that book, if you, so the he's who is probably right now also in charge of writing the maintaining the man pages of Linux. At least for some time he maintained the man pages, so he writes it, and it seems to be a very authentic book. And there only so I got the whole information from the book. So but the data structure is missing, so hopefully I'll be able to show you the data structure also within a week time. Okay, so let's come back to the slides. I've made some modifications accordingly. So it's a type of threads, as you can see here. This is a pure user level threads, ULT. So the pure user level threads, as it shows that the in the user level, using the thread library, you have the different, just a minute. So you have got the different threads created, but these threads are no way visible to the kernel space. So kernel never identifies it. There is no provision. So there is no mapping. So it's of practically it's of no use. And these are the advantages. You don't have the thread switching overhead. The scheduling is specific. It is specific to the application itself, and it can run on any OS, but just only needs a thread library. But there is no hardware support. There is no kind of OS support from this. So inconvenience is that if one of the thread gets blocked, that means the kernel feels that the whole process is blocked like that. So the rest of the threads, even if they are in the running mode, they cannot be scheduled because the existence of the threads is completely invisible from the kernel end. Okay, so let's come to the pure kernel level threads. Sorry, this was a user level thread ULT, and this is the KLT. So it's a pure kernel level thread. So in the pure kernel level thread, what happens? You create the thread, you create multiple threads, but you are creating the threads using the kernel routines. So sorry, here, so there is no thread library but an API to the kernel thread facility. So using some APIs, so there is no user level library, but using some API you can create kernel level threads. So you are creating kernel level threads. It's something similar to the creation of the processes. So through that you create, and these threads are scheduled by the kernel or the operating system. They are maintained. Context switching is uh, definitely switching overhead is high, and however, this advantage is you can actually exploit the existence of multiple CPUs because the kernel knows that there are multiple CPUs, and to have this facility enabled, like you can actually schedule multiple threads as the kernel sees to the multiple CPUs. You need some hardware support also. So in fact, as I mentioned in my last class, that Pentium and all, I mean Intel and all came up with processors which supports multiple threads to run simultaneously in their different processes, in their different cores. So that too came from mid 2000. So from mid 2000 there was some hardware support. The OS also implemented the thread libraries in such a fashion that the user level threads can be, can exploit the CPU. So everything were tuned accordingly. But this is one pure kernel level thread, and there is no user level library that supported it. Okay. However, there was a combined approach, which is a hybrid thread approach. It combines ULT and KLT. And here what happens, say using some user level library, say for example pre-thread library, you create 3 threads, but at the same time you have got some other APIs through which you actually map these user level threads to some of the kernel level threads. Okay, so these are kernel level threads, and there is a lightweight process through which you make this mapping. Okay, so corresponding to this, so if you have got 3 user level threads, you can map them to 2 kernel level threads. Okay, that means maybe this will be independent and these two will be tagged together. So if one of them is blocking, the other one cannot work. However, this being independent, it can work of its own, like that. So this combined ULT KLT approach is often used. I mean, the pure KLT approach was used in Windows NT and OS 2, but this combined ULT KLT approach was used in Solaris. Okay, so here the thread creation is done in the user space, but the bulk of scheduling and synchronization of the threads is done in the user space, and the programmer may adjust the number of KLTs. So based on the application, you can have your mapping defined accordingly. Okay, and here the idea is the lightweight process. I mean Solaris implements using the lightweight process. So in fact, Linux also uses that philosophy. So it will create some lightweight processes to which those user level threads are mapped. But the difference here with respect to Solaris is, in Solaris you can have M to N mapping. You can see that 3 is mapped to 2 here. 3 is mapped to 2. However, in Linux it is 1 to 1. So one user thread is mapped to one kernel thread, or you may prefer to call it as one lightweight process. Okay. So this is just a summary of what I stated, the whole story of the thread implementation in Linux. The POSIX, sorry. So the POSIX this specification, along with this specification, the thread standardization started, and it was available in most of the Linux distribution from this POSIX specification. And Linux first acquired the thread support in 1996, and with a library often named as Linux threads. This was what I was specifying. So this Linux threads is the implementation of the POSIX library which it supported. Okay, so Linux came up with the support uh, of the thread implementation, the Linux threads, and it has got it was a very early project, and so that actually investigated how the kernel, the primitive Linux kernel, need to be upgraded or modified to cope up with the threads. And that is the question you some of you asking, that how the data structure will handle it and all this. So that was a debate that was going on in those late 90s. And also the policy, like whether multiple user threads will be mapped to variable number of, so it will be M2N mapping or it will be one-to-one mapping. So all these issues were there. So there were several limitations also, because it's a very early design. There are several discrepancies that it suffered from what POSIX was standard was defining, and there were several performance issues also, because if the data structure was not well tuned or well written, uh, because it's a new demand that was coming those days, and the multi-core systems were about to come. So performance was also an issue. If the design was not good, the data structure, the performance suffers. And the major issue that people debated was how user level threads should be mapped to kernel level threads or kernel level lightweight processes, say for example. And in 2002, the NPTL became a new standard, and which was first got the release in Red Hat 9, Red Hat Linux 9. Okay, was a project which took a few years to came in existence, and there was a paper which was written much early, like almost like 10-20 years from now, that talks about this native POSIX thread library, NPTL, short form of that. Okay, so Linux thread was implemented. I cannot recall the name. I read it, but and this NPTL thread also was implemented by few people, a team. And then by this time, as you can see, the mid of 2000, both multi-core systems were available. NPTEL was a part of the Linux kernel. Suitable modifications was done in the kernel, and that is the reason why this from this kernel version 2.6 onwards, you have this NPTEL support, because the previous kernels, the data structures that they implemented didn't support this lightweight process creation, or in other words, a thread. Okay, so it is from kernel version 2.6 onwards, uh, considering the suitable modifications, this NPTEL came up with the thread implementation, and which was in say it was in conformity with the POSIX user interface library. Okay, and in the multi-core processors, it is in the multi-core processors only where you actually it is physically possible to execute multiple threads simultaneously. So without these multi-core processors, there is no point of having a multi-threaded application. And previously, like prior to 2000, the single core CPUs mostly, I'm not talking about the servers, mostly the desktop machines and all, the simultaneous execution of threads was just a clever, efficient illusion. I mean, it was not doing anything in practice. So pthreads is a user level interface specification, and it is not an implementation. This is an important point to note. This is not an implementation. So how this pthread library will be implemented in Linux might differ the way it was implemented in Windows, or in it was implemented for Mac. Okay, so we are specifically talking about Linux level implementations. So here the options with the designers were uh, option 1:1, where one user thread will be mapped to one kernel thread, or M2N, where m number of user threads may be mapped to n number of kernel threads. So this M:2N was actually adopted in Solaris, as we found, but this one-to-one mapping is actually followed in Linux to make things simple. Probably this was a more flexible design, M is to N, but this is a much simpler and still good enough for running. multi-threaded applications. So Linux designers preferred it. So in Linux, the pthread is implemented as a lightweight process. So this is a key point to note. And this was made possible because of the changes made in the kernel version 2.6 onwards. And the details of how it got implemented, it was using the according to the NPTEL implementation. That was a project, as I mentioned already. So which actually used a one-to-one threading model. So NPTEL is a one-to-one thread library, and in that threads created by the, so this is what I just now mentioned. So pthread in Linux implemented using NPTEL can take the advantage of multi-core CPUs. Okay. And finally, this is the point. So which we'll be trying to we'll explore more on this point. As it says, the last one, the NPTEL uses clone system call to implement user level user thread as a lightweight process. So what exactly clone does and how it differs in different variations, and how it helps to uh, uh, implement a thread request from the user level, we'll see that. So let us, so let me come to the, can you see this code? Is the code visible?
Yes, sir.
Yes, sir, it is visible, sir.
Okay. So just highlight on this. So earlier, we all know, we have extensively discussed about fork. What is the purpose of fork? The fork, by calling fork a parent process, actually is able to create a child process. That's all. So the child will have its own PID, different from the parent, and what essentially it means, the child will have no, almost no overlap. In fact, it will have zero overlap with respect to the parent in terms of the resources, in terms of entities that it will be using. So it means that the child will have its own virtual memory, it will have its own stack, it will have its own heap, it will have its own say file descriptors and all, but might be they will be pointing to the same open file table, the same entry, but it will have completely different, I mean it will be a completely different entity. But initially the point is, initially the entities are copied from the parent, but it will be running independent of the parent. So it is a complete different existence of the parent. Now apart from fork, there are many other ways also to create child processes. One is vfork, one is exec, different variants of exec, and the other one is clone. So as you can see here, I think in the line number 25 you see there is a call. So this clone is a system call, and this clone, its purpose is similar to fork but not exactly same. And if you look into the parameters, you see fork accepts nothing, because fork knows that I just have to create a it's a copy of the parent with the initial values be the same, and then it will be independent. That's all. So you don't have to put too much of information. You have to pass the information when you are calling fork, but in case of clone it is not the same. So as you can see here, the clone, the first argument is what? Can you see? It says do something. So what is do something? Can you look into this code? Is the code visible? What is do something? You go up and see in line number 14 to 17. What is this?
Sir, user defined function.
It's a simple function, right? So in the clone you have to pass a function. So what do you expect here? So clone, definitely the objective is to create a child process. Okay. So what the child process will execute, in case of fork, what it executes, we know that we can write it in the same code, and we differentiate it using the value of x, the value that fork returns, right? That is how we differentiate what the parent will do, what the child will do, whether both will do the same or not, whatever. But in case of clone, when you create a child process using clone, the code that the child process will be executing, you have to put it entirely in this in a separate function, and you have to pass on the function when you call the child creation, right? So this do something is actually the function which will be executed by the child process. So you have got a nice way to, say, actually put the whole thing here. So we have got a function. So this child process, whenever it is created, it will be executing whatever it is there in the function, and if the function is returns, means the child process is over, right? And what else you have got in the next, the second argument? Can you see what is this? Is some kind of stack, right? So why we need us? So this hints that this new child process will have its own stack space. Why it is required? Because whenever you run a function, that function might call other functions like that. So whenever there is a different function, you have to handle a execution within a function, you have to have your own stack space, right? So this is the stack. So you basically, as you can see here in the line number 20, you have malloc, you have allocated dynamically some space, and that you are passing here plus the size. So you are basically passing a dynamically allocated space which will be actually used for running this particular function when the child runs this function. And this clone VM, this means whenever you are trying to create a clone, the child process a clone of this parent process, then you are basically sharing, both the child process and the parent will be sharing their virtual memory. And this is something strikingly different from the way the child process are created in the fork. Is that fine? So in the third argument, this clone VM, you see, here is the change. So here we are forcing the child to share the same virtual memory space along with the parent. But the rest of the things are all separate. So you are trying to create a child which will not be completely independent. It will be independent but partly dependent on the parent, or partly it will be sharing the resources, and that is in terms of the virtual memory, but it will have its own stack, you see. And the code that you have put together, you have written the entire code, and you have written a function, and you are just passing the address of the function, that's all. Okay, so if the clone is successfully creating a child, then so there is a small error code and all this. So it's a parent ID and all this. So this is how it writes. So what you write here, you see, in the parent ID, so in the line number 29, if I display the parent ID, so whose parent ID which parent ID will be displayed? What do you expect? In the line number 29, if I display the parent ID, get PID, so what will be displayed? It will be the parent process ID, right? The parent which is which we are considering, which has called the clone system call. But this get PID in the line number 15, which PID do you expect it will be showing?
So the clone process, child process.
And because clone is expected to create a separate child which is independent, what we expect here, they should be same or different. What do you expect? Do you expect both to be the same?
No, sir.
They should not be the same. Let's see how it works. Okay, so what we have, GCC, what was that, clone VM. So what is this? So if I, what you can see here, what are the entries corresponding to the parent and the child, whatever we have done? What is the parent ID? Can you see the
145, sir.
145? And what is the child process ID? It is 140.
146.
So it is 145, 146. And can you see the PPID? So PPID is also, so it says that 146 is indeed a child of 145. That is fine. But what about LWP? What is LWP? What it stands for? This stands for the lightweight process, right? Got the point? So this process itself is, I mean, this is just one process, one lightweight process, whatever you say, it doesn't matter really, because the parent process ID, the parent process, its LWP code is 15145 and the child process 146146, like this. We'll see the difference within a short while. And what is both are running, both and what I have done after the creation, you see, this goes into an infinite loop and this also goes into an infinite loop. So what actually it happens, the child process after printing this, it goes into an infinite loop, and the parent process also after executing this, it goes into an infinite loop. So they are basically both using the CPU. You see, it was 8592, now it become 9293. So more or less they will be having the equal share of CPU throughout. So, and this will go on like this. Okay, now see the change here. So can you see this piece of code? So what it says, it will again use the clone system call, and it is used here in the line number 38, right? So can you read this, what it writes? So what is the child function? I have called it as child function instead of do something, and I can give a ampersand. I may not give an ampersand. If I specify the function name, it will be passing the address of the function, right? So here what I pass here is uh, the function to be executed, and what is next, again the stack, and next to it what is there, apart from clone VM, I have included here clone thread, and that is more important. So clone thread will again putting this flag while creation of a child process will create a child, but it will do it in a something different way. Okay, and more or less the rest of the code is almost the same. And as you can see here, this is a stack that created, and here is the child function. It says that it's sleeping, and that is what it does. Okay, is the code clear? Hello? Are you getting the code? Hello?
Yes, sir. Yes, sir.
So the only change, as I mentioned, I have just included, apart from, so this and this also is considered to be another flag. So it basically says that how you are going to create the child process. Okay, so rest is more or less the same. So let's see if I run this, then what happens actually. So let me terminate this previous one. Okay, so these are starting showing the displays and all, and now see what happens. Now in the PID, who is the parent process? What is the parent process ID? What is the parent process ID?
157.
What is the child process ID?
157.
Yes, so there is no change. Got the difference here? Have you got the difference?
Yes, sir. The LVP
But
is
there is a difference. But the point is, now you say that they are indistinguishable. So if you don't give the ELF command, you will probably not be able to see the lightweight process IDs, and that will make the things are same. So they are two runnable entities, but they are identified by the same process ID, right? Are you getting the point? You see,
Yes.
here it was 145, 146. Now it is 157. Both are same. So why it is happening? So that V thread, sorry, that clone VM thread, it has created a trick. I mean, it has made those provisions. And in fact, this way of creating a child process, it was not available before the client, before the kernel 2.6 version. It was not possible at all. Okay, so prior to that, there was some support using the Linux threads implementation that was done, but it was a bit more messy implementation, and it has several other issues why people have discarded it. And this is now the present So this is using nptel. So nptel uses this way of creating threads. Now you can see, now you can really claim that okay, now so this what you have actually done, you have created a thread, or if you prefer to call, you say it's a lightweight process that has created. So the original one, its id are the same 157 157 you see, but for the child process it has the same pid of 157, but the lwp id is 158. Got the difference? Is that fine? And now it has actually terminated because we didn't put the for loop here, I mean infinite for loop here. Okay, so have you got the difference now? Hello, is the difference uh, clear to you? Hello, Sampark, can you hear me?
Yes, sir, we have understood.
Okay, so let me come to the thread example now. So before we come to that, just a minute. So now in the POSIX thread library there are lots of functions, but I'll be talking about only the three, and I'll be wrapping up the class within 5 minutes. So there are three codes. One is the pthread create. We'll just see that how it works. So there's a pthread create function, there's a pthread exit function, and there is a pthread join function. It's not a system call. So this pthread create, actually it will be calling internally the clone system call to make this happen. Okay, the way we have implemented it. So what it so how many arguments are there? One, this is two, this is three, and four. There are four arguments that pthread create accepts. So what is the first one? This is the thread id. So this thread id, you see, this is a user level thread. So this thread id is not going to be the same as that of the lightweight process id. So this is different. This is maintained, and this is actually done in the user space. So this id might be 5019 or whatever, but this id will be actually mapped to the lwp process id. That is done by the nptel library, nptel implementation. So this is so we are passing what? We are passing the address of the thread id. So pthread underscore t uh, is a data type which stores the pthread ids, right, as like pid underscore t. So you have to pass the address of it because it is a pointer variable. So if you pass the address, the this pthread create will store the thread id created within that. And then we have the attributes. Attributes means this is generally we can specify it as null. So initially we consider it to be a null. So these attributes, but we can set many interesting attributes to fine tune the creation of the threads as you wish to customize. And the third option is what do you expect from this? What do you guess? It's a thread routine. So what is this? So this is the code. This is a function which includes the code that the thread will be executing, and this is the actual the function address which will be passed to clone also. So this will be actually passed as a first address or a first argument of the clone, because that is important. So if you are using clone, you have to specify what the child will be executing, and this is where you pass it here. And what is the next one? So there should be some provisions, because if you are calling a function, so the function might have some arguments to use, input arguments. So the input arguments you can't pass it here. So the input arguments will be passed in the last argument, as the last argument, and there you have to pass it as void asterisk. If you have got multiple types, an array or whatever, you have to just pass it as a void pointer to void. And accordingly within the thread function you have to retypecast it before you can use it, because from the void type you have to typecast to integer type or integer pointer type or uh, character or whatever. Okay, so this is all about that. And this pthread exit, what it says, it will pass address of a integer, and within that you can pass uh, in fact pthread exit will be calling it. So pthread exit will be called by the child function. or the thread function as the last statement. So that means this, when executed in the child function, I mean this function, this thread will be terminated. It is something similar to the exit function call system call for process. And in the exit also we know that we can pass the status code. So here this return value is something similar to the status code. Okay, and finally the pthread join, which is equivalent to the wait system call. So this pthread join, what it says, which particular thread id you would like to join with, and the return value. So this is also something similar to that of PID, to wait PID, because in wait PID you can specify the process for which you want to synchronize, like this. So which of these functions the parent thread will be executing? Which of these functions the parent thread will be executing?
Create one.
Hello,
The
pthread,
create one.
the pthread create,
And the join one.
so definitely, because it is the parent who can. So joining means the parent is going to synchronize with the child threads, right? So whenever the child terminates, it is going to synchronize with them. And who is going to execute the pthread exit?
The child process.
The child process. In fact, to be specific, the child function, the function that the child process executes, within the function the last statement should be the pthread exit. If you don't give it, you will not be able to when it's synchronized, you will not be able to retrieve the status code. That's the point. So just let's see the code for this. So here, so I'll just finish the class with now. So you see here, this is, look into the line number 31. Can you see? So line number 31 is a pthread create, and this is the thread id. So how many threads I am creating? I am creating number of threads 2. And what is this? Pthread underscore t. This is something similar to pid underscore t. So these are not simple integers, these are special type of ids, and it's an array of this threads is an array of pthread underscore t. So we can store here multiple thread ids. So these ids are user level ids that we mean, not the lightweight process ids, right, in the kernel. So we are not interested what the kernel does, just we know that what the how the kernel can handle it. So we are passing here. So in a for loop we are creating 2 or 4 or 5 threads as we require, and when we call this pthread create, we just pass the ith element of that array pthread threads I. This should be null by default, and the change of it I'll discuss in the next class. Then the thread code. So thread code is the function. Here you see in the line number, from line number 9 to 13. Okay, so from 9 to 13 you have got the thread code. The thread code, you see, you have no provision here in this argument. In the thread code you don't have the provision to pass arguments, so you basically pass the arguments here, thread arguments. So thread arguments, what we are passing here, we are passing integer values. So the 0th say element is passed when the 0th thread, the first thread is created. The second argument, the second value of this array is passed when the second thread is created, like this. So threads args I, and we have to pass the address of that. So when you pass it, you see in the thread code in the line number 9, you see these are accepted as void asterisks instead of integer. So because we know that this is indeed an integer value that we have actually passed, within the child thread function, the first step should be to recast it to the integer type. So we have recasted it. Okay, and after that there is, it's sleeping for some amount of time, displaying the some information, the thread index and all, and going to the for loop. Okay, so in that way, if we try to create the threads, in this case 2 threads, and what the parent after creating the threads does, you see this is pthread join. So pthread join, the parent calls, and it joins with the first thread and the second thread, and this is null. So why it is null? Because in this particular case we have not considered that the child is returning something. There is no pthread exit here. We have just opted not to use it, and because of that it is just passing null. It ignores the return value here in the line number 41. Is that fine? So let's see how the code is running. So this is GCC thread. What is that? Thread example. So now if we just run this, it will not be able to identify this pthread create and all. So what we need to do is we have to link the thread library, pthread library. We have to link it like the math library. Then it will work. Okay, so keep it in mind. If we run it now, creating thread 0, creating thread 1, all the threads are started and all this, it will come. So if we display here PSELF, what do you expect? How many distinct PIDs you will see? You expect to see the original parent process thread is there, and you have requested to create 2 child threads. So how many parent process IDs you will see in the second column? Hello? Can you hear me? Hello?
Sir,
Hello?
not sure.
Yes, sir.
Sir, only one.
Only one, because you see this. So what do you expect? If I call pthread create, what it is actually calling internally? The clone. And clone in what form? VM threads. And VM threads, what it does? It creates actually lightweight processes, and all those lightweight processes will be sharing the same PID, right? Because they are part of the same process, heavyweight process. You see, it's 173, 173, 173. Can you see this? However, this LWPUC 173, 174, 175. So this 173 is the uh, corresponding it's corresponding to the parent thread, you can say. 174 and 75, these are the child threads. However, they all have the same PID. And now you can distinguish. You can say that the heavyweight PID. It's not the lightweight PID. Are you getting the point? Have you got it? Hello.
Yes, sir.
So this is the difference. So now you see, if I don't give this option, if you just look into this, you will feel that there is a single process, but it's not the single process. In fact, and you can see that each of these, so in this column C, you can see the utilization of the CPU by this particular process. You can say it's a thread, or you can say it's a lightweight process. It utilizes 92% of the CPU. It uses 90%. It uses 91%. How many cores are there? Say in my laptop there are 4 cores. Okay, so 4 cores, we have got 3 processes running. So more or less each of them, they will be utilizing it completely, nearly 100%. So overhead is there. Okay, so can you say, if I, so the last thing is, if I make it 20, if I create 20 threads, can you tell me that what will be the utilization of the CPUs? What is going to be the utilization of the CPUs? How much do you expect? I've got 4 physical cores, physical CPUs, and I have created 20, including ones 21 execution threads, or execution units. So what do you expect to be the uh, utilization corresponding to each of those?
So it will kind of go in round robin. Some will have 100, around 100%, and some will have around 0.
No, I mean they are all, they will all have a fair share of this, right? Because they are all independent. So in a queue, we have already talked about it. So in the, so they will be considered to be user level processes, and they will be moving up and down. Their priorities will change, and base value will remain same. So they
So,
will be
sir,
utilizing the CPU in the similar way. So my point is, a particular process, how much CPU share it will get. So this says that 173 is getting 92% of the CPU share, and same as the other two also, they are more or less the same. But if I schedule 20 or 21 such processes, or I mean say lightweight processes, if you would like to use the term, or threads, I have got 4 CPUs. So how much of CPU utilization each one will experience or enjoy?
Sir,
First of
about
all,
20,
I mean, we don't know. Huh? Sorry.
about 20%.
Yes. So let's see that. Hopefully, it will be 20%. Can you see the figures? This is 23, 19. So it has not yet converged. So some are 20, some are they are, there's a subtle difference because, but if you keep running them for a long time, you will find that they will more or less converge to 20, 19, 21 like this. Why it is so? Because you see 20, 21 processes. So each core, each physical core, how many threads hopefully it will be executing on an average?
On an average, 5.
5, sir.
5, 4 or 5, and 5 each means how much CPU it will be, each of them will be able to get, acquire?
Around 20.
Around 20. So that is what is happening, you see. Okay, so this is the, so this actually shows, we can have a feel of uh, how many that these user level threads that we create in the using the user library are indeed realized as kernel level entities, schedule level entities. In Linux, we may prefer to call it as a thread, we may prefer to call it as a lightweight process. They are really distinguishable, they have got their independent IDs, and they are separately schedulable also, right? And there are provisions in the data structures which will accommodate them as independent entities, but still they are having a lot of overlap in terms of the virtual memory, in terms of other things that we have already mentioned in my last class. Okay, and the one more field is NLWP. What is this? Can you interpret this? What is what this is actually? This is 21, 21, 21. Here it is, you see in the previous example it was what, 333. What it means? So it's the
Total
number of lightweight processes under that banner. So it says that there are 3. So if I write here top, so how many threads are actually executed in the system? There are, see, there are total 28 threads. You see there is a, so it's clearly specifies threads. There are 28 total threads, and 22 are running. How this 22? Because one is my parent thread and 21 are my child threads, right? And 6 are sleeping. So which are those 6 sleeping threads? Which are those sleeping threads? And in this case, in the, this basically shows all the running threads here. So what are those sleeping threads? They correspond to, you see this one, this root, and then other, like you see this init and all this bash and all this. So they are all sleeping. Got it clear?
So
Is that fine?
PID, sir.
Which one?
So in the top command, the PID is the lightweight process ID in the top command. So scroll up.
Just a minute. Yes. Now this is the lightweight process ID. This is showing the lightweight process ID. You see here it is, when you see this is a PID field. This is a PID field, and here it is all 183. And here in the top, what is shown as a PID field, this is actually the LWP ID field. This LWP identifier. You see? Got it? These are the LWP IDs here. Hello? and they are all independent threads, and that's why the total number of threads are that exist in the system is 28. And this also includes, in case of say bash or root, they have not created any threads, say for example. So here the that is a process, that is a thread, but that is sleeping. And one more point is here, you see in the root what happens, the root PID has actually created one child thread. You see in the second line, can you see second and third line, the init process, the init process 1 PID 1, it has created one lightweight process with the name 5. So it's entirely in the kernel space itself. It's a kernel, this thread is created by a kernel process in the kernel space. As we are doing it in the user space, that has been done in the kernel space. Maybe by calling clone, init has created one child thread. Is that fine? Okay, so this much for this class. Are there any questions? Do you have any question?